Okay, everybody, today we're going to look at something called an exponential function. So it's a type of graph, a parent graph, that uses a variable, the x, up in the exponent. So the reason we call it exponential is the location of where that variable x is. So anything that has a variable and exponent, that's what we call them, exponential. So in advanced algebra, you talk a little bit about these as well. So this lesson today is to help you just remember, what does a parent graph look like if it's exponential, and how does it behave if we do transformations, if we move it around. So we're looking at a very different kind of graph, because if the base is a number and the variable is the exponent, it behaves very differently than if the base is the x. So like an x squared or an x cubed, those polynomial graphs we've done before. So these will look very, very different. So we're going to talk about what all these values do. If you change the base, what effect does that have, and how do we move those around? So in order to be able to do that, we're going to start with just a pretty basic parent graph, y equals 2 to the x. And we're going to go ahead and do this just as some numerical values. If we don't know what something looks like, we're going to talk about just plot points and see what happens. So if I plug in a -2, remember what that negative exponent means, reciprocal, so 1 over 2 squared, or a fourth. 2 to the negative first would be 1 over 2, so a half. 2 to the 0, anything to the 0 power is 1. 2 to the first is 2, and then 2 squared is 4. So let's go ahead and plot those points. So I have -2 a quarter, -1 is a half, and then 0, 1, 1, 2, and then 2, 4. So if you remember from last year what the shape of this graph does, if I keep picking bigger and bigger values for x, this graph is going to continue to grow and grow and grow without bound. It's going to get huge. If I pick smaller and smaller values of x, this graph is going to get smaller and smaller and smaller, closer to the x-axis, but not quite ever get there, right? We have what we call an asymptote over there. Because you think about it, 2 to some power, whatever that is, can't ever actually be equal to 0, because it's just going to get smaller and smaller. It'll be super tiny, but it never actually gets there. So we have that idea of an asymptote. So this graph is increasing for all values of x as we look at it from left to right. So some information to fill in here. So the one that I used an example where the base was bigger than 1, and we did a 2. This would be the same if it was a 3 to the x, 4 to the x, whatever it might be. So let's take a look. So for domain, what can we use for x? Well, anything we want. It would be all real numbers. Range are the outputs, the y's. Look at where the y values on this graph. Everything is above the x-axis, so that means the y's have to be greater than 0. So you can write it as an inequality. Some people prefer that as a interval, and that's fine too. Y-intercept, where does this graph cross the y-axis? Well, right at 1. Now, question, so 0, 1, or 1, would the y-intercept always be 1 for a parent graph that's exponential? Well, anything to the 0 power is always going to be 1, so it would be for sure. So as we look at these graphs, every parent graph for an exponential should have a y-intercept of 1. All right, behavior. So we talked about the just general behavior, it's increasing, but I want to look at end behavior. Y approaches what as x approaches infinity, and y approaches what as x approaches negative infinity. So as we look at the ends of the graph, what's going on? So let's take a look. So as y or x gets bigger and bigger and bigger, so as we go this way on the x-axis, look what happens to the graph. It grows and grows and grows. We keep timesing by 2, doubling, doubling, doubling. So it's going to keep getting bigger and bigger, so y approaches infinity as x gets bigger. Okay, so let's look at the other direction. As x gets smaller, so going this way, what's happening to the y's? Well, they get closer and closer and closer to 0. They don't quite get there, but they get smaller and smaller until they get closer and closer to 0. So as x gets small, the y values go towards 0. So that same basic shape will always happen for an exponential graph with a base bigger than 1. Okay, horizontal asymptote definitely has one, but only on this side, right? So it's the negative x-axis that it's approaching, not the positive. So I'd probably say negative x-axis. And then is there a vertical asymptote? Well, no, there's no undefined places on this graph. There's no vertical break. So these parent graphs just don't have that. All right, so I want to compare and contrast this to, okay, those are bases bigger than 1. What happens if the base is less than 1? So I want to take a look on the same axes now and graph an equation where the base is less than 1. So I'm going to have you take a look at 1/2 to the x. All right, so we're going to do the exact same thing. I'm going to do the same values. So we're going to do 1/2 to the negative second. So 1/2 to the negative second. So think about what that negative exponent means. It means reciprocal, so that would be 2 squared, or 4. Then we have 1/2 to the negative first. That would be 2 to the first. 1/2 to the 0, that would be 1. 1/2 to the first, that would be a half. And then 1/2 squared, that would be a quarter. So let's go ahead and graph that on the same axes here. So we've got -2, 4, -1, 2, 0, 1, 1, 1/2, and 2 1/4. So we get a graph that looks something like this. So this would be y equals 1/2 to the x, and then that green one, the original, would be y equals 2 to the x. Okay, so I want you to compare and contrast these two graphs, the green one and the blue one. What relationship do they have with each other? Well, they're a reflection over the x-axis. Or the x-axis, sorry, the y-axis. So the reflection over the y-axis. So if you think about the y-axis here as your fold line, one would fold right on top of the other one. And what I want you to think about is why might that be? So if you think back to what makes graphs reflect over the y-axis, if I can rewrite this expression instead of 1/2 as 2 to what power? So 1 over 2, that would have to be a negative exponent. That's reciprocal. 2 to the negative first, or that's the same thing as 2 to the negative x. If you put a negative with the x, if the x changes sign, you're going to flip over the y-axis. So really, 1/2 is the same thing as 2 to the negative first. That will give you that reflection. So these bases less than 1, these graphs that are decaying or decreasing as you go left to right, they're really just doing a reflection over the y because of that value that we can do with the exponent. So different way to think about it, but it's the same graph. So if your base is less than 1, we have very similar things that we can talk about. So I'm going to go ahead and take a look at the bases less than 1 now, just kind of wrap up and talk about what we know about them. So the domain, again, is all real numbers. The range is still going to be everything that's positive, however you want to say that. And then the y-intercept still 1. Behavior now. Y approaches what as x approaches infinity? Y approaches what as x approaches negative infinity? Let's talk about that. If you look at those two graphs, the blue one now that we're doing now is doing the exact opposite to what the green one did. So where the green went to infinity, the blue now goes to 0. And where the green one went to 0, the blue one goes to infinity. So these are actually just flip-flopped from what they were for our other graph. So y is going to get closer and closer to 0, the bigger x gets. It's decay. And y is going to get bigger and bigger, the smaller the value of x gets. So we have that same idea. So instead of being the negative x-axis then for the asymptote, it would be the positive x-axis. And again, there is no vertical asymptote. We don't have any breaks in the graph. Okay, so we're going to kind of walk through. Now we know that the basic stuff is doing, depending on the size of the base, we know bigger than 1 and between 0 and 1. Now let's talk about as you change those numbers. So I'm going to have you on your graphing calculator, so go ahead and you can pause the video, type in these 4 equations on your graphing calculator and see what that looks like. So go ahead and pause so you can type those in and we can talk about the comparisons between them. So when we're looking at being able to decide what those graphs are going to do. Oh my goodness, I don't know what my calculator's doing here. We can make a decision as to what that base actually does in our equation. So we can figure out what that looks like. So go ahead and pause and see if you can come up with a statement you could say. As you change the base, what happens to the value or what the outcome looks like on the graph? So as that base gets bigger, what does the graph do? So if I take a look at mine, so can compare to what yours is. So we have 2 to the x, and then we have 3 to the x, and we have 4 to the x, and then we have 5 to the x. So as you look at all of those graphs, it would appear to me that the bigger the base is, the steeper the graph ends up being. So as the value of b, the base, increases, the graph gets steeper. Now I wonder why that is. Well, think about what you're multiplying by. So 4 to the x means you're timesing something by 4. So for example, 4 to the second power is 16. 3 to the second power is only 9. So timesing something by 4 is always going to give you a bigger outcome than timesing something by 3. So the bigger the base, the steeper the graph is. So we can adjust the steepness of these graphs by changing the parent graph. So what is that base that we're using? Are we doubling? Are we tripling? Quadrupling? Whatever that might be. So that's one way to transform these graphs. Another way to transform them, though, is to look at numbers that we can put in place of all of the other things that will move graphs up, down, left, right, and all of that. So not just manipulating the base, but looking at other numbers that we can put in there. So under these transformations, we have three basic types that we talk about. So we talk about things called translations. Those are like slides, left, right, up, down, those kinds of things. Dilations, and that has to do with things like if you've ever been to the eye doctor, you put those drops in your eyes. If they get dilated, your pupils get huge, right? And then you can't see, and you have to, it's crazy. So dilation has to do with the size, so it's stretching and compressing. And then reflections, flipping over something, a line, so we can do it over the x or the y. So what I'd like you to do is try to come up with examples of equations that would do each of these. So I'm going to have you go ahead and pause the video. We're going to use 2 to the x in a second here. We're going to use 2 to the x as our parent graph, and we're going to decide what kinds of things we can do to make the graph move left or right. So if you can figure out different graphs and equations, so if you type them in and kind of guess and see if it does what you think, and then I'm going to go through an example of each one as well. So pause the video, see if you can come up with equations that do each of these things, and then just kind of listen in, and you can double check and see that your thinking is on the right track. This is all stuff we've talked about before. Okay, so here are some for me to try. So if I want to make a graph go to the left or right, that means I have to have it with the x value. So if I did something like this, so with the x, that means up in the exponent, this would be going to the left 1 because it's a plus 1 in the exponent, so that comes from minus a negative. So if I wanted to go to the right 1, it would be minus 1. So just be very aware where that value is. It has to be up in the exponent to go left and right. So if I want to go up or down, it has to be outside. So if I do something like that, plus 1, that would be going up 1. Or if I wanted my graph to go down 1, that would be on the outside. That would be going down 1. So the add or subtract on the outside, that moves your graph up or down. We've done that a lot. Vertically stretching, those are coefficients multiplied out front. So if I want to stretch the graph, I'm going to have to multiply by a number out front that's bigger than 1. So if I times something by 3, it's going to be 3 times bigger than whatever that 2 to the x answer was before. If you want to compress, you just need to multiply by a number that is less than 1. So something that's going to make that value less than what it was originally. Okay. Reflecting over the y and x-axis. Let's do the x-axis first. If you want to flip over the x, the negative sign goes out front. Why is that? Because we take the output of our answer, the 2 to the x, and we take the opposite sign. So that means if it was positive, that y value would become negative, we'd flip over the x-axis. If we want to flip over the y, we already talked about that one today, 2 to the negative x. If I put it in with the x value changes sign, which means you'd be flipping over the y. All of these things that we've done have the same effect on these parent graphs as they do on any other. So we're going to real quick go through a few examples of how you might want to graph something like that then. So here's the parent graph we were just talking about. This would be an example of going left 1, because remember that comes from minus a negative up in the exponents there. So we're going left 1. So you could go and make a table of values by hand. So you could go ahead and do one of these things and plug numbers in, and that's great. You could take our original parent graph and just slide all those numbers back 1 to the left. What I think a really common way to do it would be just to go into your graphing calculator, because I know you can plot points if you need to. Use the technology to help you just to make this a little bit faster. So we're going to actually go in. I'm going to type in my equation. So 2 to the x plus 1, make sure that entire thing is up in the exponent. And then I'm going to graph it, see what it looks like. So there's no surprises. So that's that graph shifted to the left 1. And where in my graphing calculator can I find points? We'll just go to your table. So we'll be able to get some real quick and easy values to make sure we know what that looks like. So we're just going to get a few things from that table to be able to do this pretty quickly. So negative 1, 1, 0, 2, and 1, 4. And we can get a nice approximation of what that graph looks like. So what my key thing is for you is I want you to be able to do this. I know you can type things on your graphing calculator and graph, or graph by hand if you need to. My big thing is that you understand what the numbers do, what the transformations are, so you can visualize that. Okay, so take a look at how this one might be similar and how it might be different. First of all, the transformation, minus 1, that means the graph is going to go down 1. So now think about what happens to those asymptotes. Normally I'd be approaching 0. Now if I move the graph down, that's going to affect where that asymptote is. Why didn't it affect it on the last one? Well, we moved it left and right. If you move a graph left or right, it's not going to affect where that horizontal asymptote might be. But if I move my graph up or down, definitely will, because now my horizontal asymptote for that graph is going to be down 1. So we have to keep track of that. Here's the other thing that's different that I hope you noticed. It's an inequality now instead instead of an equation. So how is your graph different if you have an inequality? Well, now we're going to have to do some shading, right? There's a whole region that are true or make this inequality happen. So if it's less than or equal to, what do you know about the curve? Well, it's going to be solid, which means those points are included in the solution. They make it true. So all the points on the actual or included, I guess I can say, all the points on the curve are part of the solution set. And then if it's less than, do you remember where you shade? You actually shade below, because it's all the values, the curve, that are below the curve that would make it true. Now remember, if you're not sure where to shade, you can always test a point, right? Just try it and see if it works. If it does, cool, then shade that direction. What if it doesn't work? Shade the other way, right? So you know which value you're going to do. So again, if you want to go ahead and use your graphing calculator to help you get some points on here, just to make this go a little bit faster, it'd be 2 to the x power, and then make sure you get out of that exponent -1. So just be careful on how you're typing that in. It's really easy to kind of miss that. And then go ahead and graph just so you can see the picture. I think that's helpful. If you trace on your graphing calculator, just to see what's happening with the x values, if you trace to the left, as x gets smaller and smaller, it's kind of interesting to look at what the y's are doing. They're getting smaller, negative 0.96, 0.97. We get down to negative 0.99. Theoretically, we know it should never actually get to -1, but just realize the more you trace, at some point your graphing calculator might actually say -1. Do you know why that might be? Well, at some point it's going to have to round, right? It can't handle that many digits. So if it actually says it, that's what's happening. It's not that it actually equals -1, but it's just it can't handle that many digits on there. So go ahead and go to your table so you can grab some data values here. So -1, -0.5, 0, 0. Then we have 1, 1. 2, 3, get some good points on there. So we said it's equal to, right? So the curve is included. Now, if it hadn't been equal to, then we would have said a dash there. And now because it's less than, I know I'm going to be shading below. So all these points that are underneath the curve that are smaller than the curve, those would be the values that make that statement true. So we can do inequalities as well. But again, the most critical thing is understanding what this parent graph is telling you. All right, so the -1. All right, so let's take a look at the next three. We're not going to actually graph any of these. We're just going to talk about them. So tell me, because you can actually, I can actually hear you because you're listening to a video. Tell yourself, have a nice conversation. What's different about this one? So what is the transformation? Well, it goes up 1 for sure. The parent graph itself is 3 to the x now, which in relationship to 2 to the x is going to be a little bit steeper. And this less than is going to tell me a couple things. First of all, I'm going to use a dashed. That means the points on the actual curve itself are not included in the solution set. Think of it like a fence. It goes right up there, but not including the fence. And then we're going to be shading below, because that would be a less than again. So if I were going to graph this one, the whole graph would be up 1, which means my horizontal asymptote would be at 1. I would be graphing 3 to the x, which is a little bit steeper, and then I would be shading below. So just kind of thinking about what would that graph look like. All right, what's the comparison between these two? Well, they're both 4 to the x, so they're both a little bit steeper than that 2 to the x would be. But what would this graph do? Be down 3, right? Because it's on the outside, it's with the value of y, the whole graph would be dropped down. Okay, and then last one, what's the difference? How would that second graph change? Well, look at where that negative sign is. It's with the x. So this is a reflection, and it would be reflected over. And careful, if the x changes sign, you're reflecting over the y-axis, which remember, the other way to write that, 3 to the negative first, that would be the same graph as decay. So if you see a negative exponent, that means the same thing as a fraction. That means you have a decay situation. So I just need you to be able to understand, what do these parent graphs look like? And how do they behave? What do these numbers do? They do exactly the same as they would for any other parent graph. So having that awareness, you should know and be able to predict what those new graphs will be.